Welcome back. In this video we're going to talk about how to visualize a directional derivative. To do so we're actually going to allow for some new functionality in Mathematica. Here I have a blank notebook file which is lesson 11 examples. I'm going to go ahead and create a new cell here and I'm going to do a subsection. So this is going to be called lesson 11 example, visualizing the directional derivative. What is really exciting about this is not a command, this is text. So if I push enter, Mathematica, actually, you hear that? That's my computer saying, oh hell no, you can't go there. This is text, so if you wanted to type mathematics, this is how you do it. So here I have a subsection. If I go down and put text in, I'm going to explain this example. So using Mathematica, draw a tangent line to the surface. Okay. Let's describe the surface. In this case, I'm going to go ahead and use the writing assistant. So here's my assistant. I'd like to say that this is, let's see here, F. And then we'll go ahead and put parentheses around this. So there's the parentheses. This is x comma y. And then we're going to go ahead and define this to be x squared plus y squared at the point. So we'll go ahead and drop another parentheses. Let's do the point 2 comma 2. And we'll put a in the direction, so this is where I'm going to close this, in the direction of the vector. Now we'll call this direction U, so we're going to go ahead and format, style, text, and of course we should go to basic writing assistant. Okay, so let's go ahead and do center aligned. And then we'll do a vector here. So now this is the vector u. And of course, when we talked about the directional derivative, this vector has to be a unit vector. And we'll go ahead and call this 1 divided by the square root of 2. And we'll just go along the line. Oops, sugar. What did I do here? Undo. Sugar. 1 divided by the square root of 2. And we'll just copy and paste. You gotta be kidding me. 1 divided by square root of 2. We'll go along the line y equals x. So 1 divided by square root of 2. Okay, so now I have my description of the problem that I want to solve. So use Mathematica, draw a tangent line to this surface at the point in this thing. Let's go ahead and do a solution. So I'm going to go ahead and format a new cell. I'll do a subsection. So this is a solution. And we'll call this visualizing the directional derivative. And that's what we'll use the notation d sub u of f at the point AB. Okay, here we go. So we know the definition of our function. So it's f sub x, y sub, y sub x. And this is going to be the elliptic paraboloid given by x squared plus y squared. Since this is a multivariable function with an explicit description, I'll use plot 3D command. I'll go ahead and name the last bracket. So this is the end plot 3D command. Okay, let's graph f of x comma y. If I'm going to do the point AB equals 2 comma 2, so let's go ahead and just put that in. A equals 2, B equals 2. And then we'll put u sub 1. In this case, we know exactly what u sub 1 should be. It should be 1 divided by the square root of 2. And then here, u sub 2 should be equal to 1 divided by the square root of 2. Okay, we'll get back to that later. If we want to have a secant line through this point, we're going to need to be able to visualize the a disk around this point. So why don't we just set the domain to be like x goes from -4 to 4, and then we'll say that y goes from like -4 to 4. And then what we'll do is we'll do the plot range to be something appropriate. So maybe we go from like -4 all the way to 16. The minimum of this is going to happen at 0, 0, and the value is going to be 0. So maybe -2 or something like this. Let's go ahead and just visualize this. So I'll evaluate this. There's my elliptical paraboloid. You can already hear me getting mad. So here I'm going to do clipping style to be false. Other thing I'm going to do is I'm going to turn the mesh off. All right, there's my elliptical paraboloid. I'd like to be able to see through this sucker. So here I'm going to go ahead and do plot style. And then what did we saw? Directive. Yep. And I think real mathematicians graph in pink. And perhaps we do the opacity to be about opacity, I don't know, 40%. Okay. And then I don't know if you up for this. I am. I'm going to go ahead and put the axis through the 0, 0, 0 point. So here I'm going to tell put your axis at 0, 0, 0. So there's not going to be a box, but instead the axis. And then some students say, hey Jeff, it's really nice when you actually label your axis. So I'm going to go ahead and axis label this sucker. Maybe you call this X, Y, and Z. Uh-oh, it's complaining. Okay, so there's my X, Y, and Z axis. I like when this thing's a little larger, so maybe I do image size, and let's go large. So that gets a little bit larger. Do we see that the tick marks are determined by Mathematica? Maybe I want to actually specifically force Mathematica to do specific ticks rather than just general ticks. So here I can do ticks, and I can have, perhaps we call them X tick, Y tick, and Z tick. And then up here what I'll do is I'll actually define each of these to be a table. So X tick, I'm going to go ahead and define by a table. And this table is going to run over the I values, where I ranges from -4 to 4 and goes up by 1, because that's the domain of my graph. The Y tick is going to be the same thing. So here I'll use -4 to 4. And then the Z tick, of course, probably should go from like -2. Oh, of course, each of these should be a comma in between, right? Should go from like -2 to 16. And maybe in Z we want the tick marks to go every 2. Okay, so that gives me the type of thing that I want to see. Okay, so now we have our surface, we have our tick marks scheduled out the exact way we want them. Let's go ahead and visualize the point A, comma B on this three-dimensional surface. So to do this, I'm going to go ahead and just combine my plot 3D command with appropriate show command. So here, we're going to do a graphics, and this is going to be in 3D. We go ahead and use a list, and we're going to do the point size since we're going to graph a point. I think 0.02 has been quite beautiful. And then we're going to do an actual point. And remember that this point is going to be given by A, comma, B, comma, 0. Okay. So notice that this, maybe that's a little too big. This point is the point at which we're going to expand. So we actually need to project this point onto the surface, right? So this is a three-dimensional visual of the two-dimensional input point AB. To project it onto the surface, what we would do is we would evaluate F at AB. Okay, so there's our point around which we're going to expand. Maybe we should do specific colors. So let's call this the red point. Here's the red point. So the one on the bottom is going to be the three-dimensional visual of the input point A, comma, B. And then the one on the surface is going to be the point along the surface that we're going to get the tangent line to. Remember that we need a second point along our line. And the way that we got the second point was to move h units along u1, u2. So for now, let's call h, the parameter h, let's set it equal to 1. And let's find a new point, and we'll do this point in blue. So here, we're just copied and pasted. We'll call this blue. Oh, sugar. We'll call that blue. And then we're going to go h times u1. And then here, this would be b plus h times u2. And then the same thing is true here, except we would want to evaluate f at this thing. So let's go ahead and do that. Okay, so what we just did is we have now 2 points on the surface. Those are our secant lines. The points down here in the xy plane are the visual of the domain space in R3. They aren't in the domain, remember. The domain is R2. These points have 3 coordinates. Now what we're going to do is let's visualize a line. So let's go ahead and take the line in the domain space. So this one's going to be a little bit more interesting. Because I need to do a line, I want to go ahead and tell, let's go ahead and define this. So here we go. Let's call point P0 is going to be the point A comma B. And then we'll call the point P in general was going to be the point, sugar. So this would be A comma B comma 0 because it's an R3. And then this would be A plus H times U sub 1. This would be B plus H times, sugar. I don't know what I did there. Times U sub 2. Okay. And why don't we call these, those are now in the xy plane in R3. We'll go ahead and define point A to be the image of P naught on the surface. So this is going to be f of A comma B. And then we'll call point B to be the image of P on the surface, which is literally just the same input. And then we would evaluate the surface at this sucker. Okay, so here we go. Let's go ahead and graph the line. So in this case, we're going to do thickness. And I always forget what thickness is appropriate. 0, 5. And instead of point, this would be a line. And the line is going to connect point P0 in R3. Oh, sugar. I think this should be a 0, not an O. To point P. What are you complaining about? Oh, Mathematica complaining that I didn't actually do this well. What else is it complaining about? Let's see. So U1, U2, 0. What did I not suppress? I didn't suppress this one. And then what else did I not do? What are you complaining about? Oh, I didn't put a comma right here. So those are 2 things. That is, okay, there it is. All right, let's do that in black. All right, and that's a little bit too thick for my taste. It's still a little too thick for my taste. I think in the previous video when we did this, we actually did this in red. So why don't we turn this, let's do the domain space in red. And then we'll do the projection in blue. So what we wanted to do is now we also want to graph the tangent line to this sucker. The secant line, and we'll do this in, I think we did this in blue actually, right? So this would be point A to point B. So now that's the secant line, which is the projection. We have yet to do the parametric curve. And in order to do this, maybe we use Parametric Plot 3D. And then here we close our bracket. So this is going to be end Parametric Plot 3D command. Here we're going to go ahead and call this A plus H times U sub 1, B plus h times u sub 2. And then, of course, the output would be the surface evaluated at these inputs. So here I'm just going to copy and paste. And I think we said that h should be some region around 0. So maybe we go from like -1 to 1 for this h value. And since this is a plot, we can do plot style. And then we call this directive, blah, blah, blah. And then I think we called this red, and then maybe the thickness is what we want to control. And it looks like 0.004 has been working kind of good for us. Okay, so there's the curve that we want to move along. What's really nice about this is we can actually change our secant line. So if we go back up to h, and maybe we call h 0.5. So now this, what are you complaining about, Mathematica? Oh, I know what it's complaining about. It's complaining about the fact that I'm using h here, but I also have h as a parameter up there. So perhaps I want to use t. It's a better way to do it. Yeah, there we go. Okay. So there's our secant line, there's the curve, and then we can kind of visualize this by taking h to be really, really close together. So maybe we say it's like 0.1. I don't know what it's complaining about. What are you complaining about, Mathematica? Should be a triple. It's complaining about something. I don't know what it is complaining about. Okay. But the point there is that you see, so let's go back up to 1. Let's see if this works. Okay. So this is a visual of that thing. Now if we wanted to get the tangent line to this thing, what we would do is take the limit as h goes to 0. I'm not actually going to do that in this video because I think this does enough in terms of how to graph. So what we've done here is we've graphed a surface. We have 2 points along that surface. We've created a secant line through those points. And then the way to create the tangent line is to let the limit as h goes to 0 of the secant line slope be evaluated. And we're going to see how to do this in the next video. But that's kind of the concept here. All right, in the next video, we're going to take a look at the effective way that we take directional derivatives without a limit. Because remember, limits are painful. Algebra is not so painful. See you in the next video.